Good morning, everyone. My name is Michala Vojtíška. I am a professor of mechanical engineering. Today's lecture is part of the course of experimental methods and measurement. It's a series of 3 lectures which is on vehicle emissions. During last lecture we looked at what are the pollutants, why are they important, why do we care about vehicle emissions. Today we will talk about how do we reduce emissions and how do we measure emissions. So, ladies and gentlemen, start your engines. Let's go for a ride. Mash it on down. Okay. Just for an overview, third lecture will be after the holidays on January 6th on advanced measurement, particulate matter, whatever we don't cover today, and on legislation. I am not quite sure how we will arrange for laboratory tour in Rostocky. We will record it on video camera with some commentary and make that available to you, and I will be available for discussion. I don't know where this will be, so please bear with us. Last time we talked about why do we care about emissions. Since this lecture was recorded, I will not go over it again. Maybe briefly. Particulate matter is responsible for premature death of about 1 out of 1,000 people with large losses. Economic, several percents of gross domestic product. And we do have technology that allows us to achieve very low emissions. And we need to make sure that we use the best available technology. We look out for incidental creation of pollutants that could be of concern, because transportation, mobility is part of freedom. It's a useful thing, and at the same time we do care about our health. The main problematic pollutants are particles, oxides of nitrogen created at very high temperatures and pressures in a combustion chamber, and those are the 2 main categories. Sulfur, sulfuric acid, lead, benzene, CO. They are much less and less of a problem because of technological advances. We have new emerging pollutants, nitrogen dioxide created in exhaust after treatment devices, ammonia created during reduction of nitrogen in catalytic devices, new pollutants like aldehydes associated with oxygenated fuels, especially alcohols. And greenhouse gases are not just carbon dioxide, but also methane, produced by engines that run on methane or methane-containing fuels, natural gas, biogas, pyrolysis gas, sewage sludge gas, and also nitric oxide N2O, which is not harmful to our health. It is chemically very stable, but it is a very potent greenhouse gas, and its production is associated with some NOx reduction catalysts, selective catalytic reduction and NOx trap. Particles produced by the engines are very small, on the order of 10 to 20 nanometers, and then aggregates of larger particles, and that size deposits very readily in human lung alveoli. That's why small particles are dangerous. Emissions are usually concentrated within tens, maybe hundreds of meters from heavily traveled roads, and those who are frequently near heavily traveled roads have higher risk of various ailments. Greenhouse effect, rising CO2 concentrations, greenhouse gas emissions, fraction of transport. So, reduction by better fuels and technologies. Just a review, we run mostly on hydrocarbon fuels, so ideal combustion results in carbon dioxide and water. In reality, incomplete combustion or incomplete oxidation of fuel and lubricating oil leads to particulate matter comprised of elemental carbon and other solid particles, volatile and semi-volatile particles, sometimes referred to as organic carbon, and then we have volatile organic compounds in gaseous form termed hydrocarbons. I would not call them unburned hydrocarbons because they are not just unburned fuel. They are a mixture of unburned fuel and various intermediate products of combustion, oxidation, pyrolysis of fuel. Then we have carbon monoxide. Besides the engine burning fuel and lubricating oil, whatever else is in a fuel comes out in the exhaust. Whatever comes into the engine has to leave the engine, or it deposits in the engine, but that causes a lot of problems. So if we have metals and sulfur in a fuel and oil, it comes out through the exhaust, most of it. Then we have nitrogen oxides, nitrogen monoxide or nitric oxide, NO is created under very high temperatures in a combustion chamber through dissociation of molecular nitrogen and molecular oxygen through thermal mechanism referred to as Zeldovich mechanism because it was described by Russian scientist Zeldovich. Nitrogen dioxide, NO2, gets created by oxidation of nitric oxide. From the engine, most of nitrogen oxides are in the form of NO. Only several percent of NO2 and increasing share with lean-bar engines are coming out from the engine. That can change in engine after treatment. We also discussed greenhouse gas emissions, CO2. CO2 is emitted no matter what hydrocarbon fuel you burn, whether you burn biodiesel or petroleum diesel. I exhale CO2. The difference between burning fossil fuels and renewable fuels is that with renewable fuels, CO2 gets taken from the atmosphere, it's bound as hydrocarbons in the plants, and during the combustion of biomass, CO2 is released, but it's a part of natural circulation of CO2. Also, all the minerals that are in the plants, if the ash is returned, can be used as fertilizer, and leftover biomass could be used for heat, and you have a circular economy. Unfortunately, there is not that much land to supply us with enough biofuels that could replace our diesel fuel, maybe on the order of 10%. We've talked about embedded energy in the fuels and well-to-wheel analysis of different biofuels. It's a subject of ongoing research, and the results are not very consistent. It is not a function just of a biofuel, but from what crops you produce that biofuel, by what process and under what conditions. And that results in tremendous differences. But generally it is possible to produce both biodiesel and ethanol with net benefit in greenhouse gas emissions. Not always, you have to watch it. So, emission reduction. First great emission reduction was thanks to a three-way catalyst, And that was on gasoline engines in the United States. Those engines have produced more nitrogen oxides per mile or per kilometer than automobile diesel engines with no exhaust after treatment whatsoever. And those nitrogen oxides got very successfully reduced. So in a three-way catalyst, we have hydrogen, which is in the exhaust, we have hydrocarbons, we have carbon monoxide, and then we have oxygen that's left in the exhaust, and then we have nitrogen oxide. And what happens in a three-way catalyst? Nitrogen oxides are reduced back to nitrogen and oxygen. That doesn't happen just as a magic by itself. It doesn't happen voluntarily. Actually, what happens is nitrogen oxides release nitrogen, and this oxygen is used to oxidize hydrogen, hydrocarbons, and CO. You get CO2 and water. So there are many processes happening. It stands hundreds of reactions. To simplify this, hydrogen, hydrocarbons, and carbon monoxide are oxidized to carbon dioxide and water. Nitrogen oxides are reduced back to nitrogen, and oxygen from the air is also used to oxidize hydrocarbons, hydrogen, and carbon monoxide. Now, very much depends on the stoichiometry of the three-way catalyst. If there is no oxygen, well, after consuming all the oxygen from nitrogen oxide, I don't have enough to finish the oxidation of hydrogen, hydrocarbons, and CO2. So, under rich condition, we get hydrocarbons, CO. Most of the nitrogen oxide is reduced, but nitrogen is also reduced to ammonia. So we have a new pollutant that is being created under rich conditions. Under lean conditions, these nitrogen oxides need something to be oxidized to take this oxygen away. So if there is not enough hydrocarbons and CO to take the oxygen away, some of the nitrogen oxides do not get reduced. So we have excess nitrogen oxides. This is why it is important to keep the engine at stoichiometric air-fuel ratio. That's why it is important to keep the catalyst operational. Many impurities in a fuel, manganese or sulfur or metals, ashes in a fuel, in a lubricating oil, those can over the time deactivate the catalytic converter. Sometimes this deactivation is reversible, sometimes it's not. This is why we switch to unleaded gasoline, low sulfur gasoline, and also with the introduction of catalyst on diesel engines, low sulfur diesel. The air-fuel ratio control needs to be within several % of stoichiometric. If you have a very clean burning engine that produces very little hydrocarbons and CO like a natural gas engine, then that window narrows down to maybe 1%. So that's the three-way catalyst. it has 99+% efficiency under optimal conditions when it's warmed up and when it's fed stoichiometric mixture. What does it mean? What are the practical implications for testing? Well, we need to cover the regimes when the catalyst is cold start of an engine, because cold catalyst doesn't work. We also need to cover transient operation, during which you can depart from stoichiometric air-fuel ratio. Under steady state condition with a warmed up catalyst, well, that's not as difficult to achieve very high efficiency. So cold starts and transient operations are challenging for design of such a system. And then in use, you have to make sure air-fuel mixture is stoichiometric and catalyst is working. And that's why we have inspection and maintenance programs. That's why we have remote sensing that's measuring emissions of vehicles as we go. Now, similar thing are happening with diesel engines. I will erase the board. Now, I will ask our students who are also participating by teams to write all the questions in the chat. And if you are watching this outside of this normal class period, or you are not our student, then you can email me your questions. So that's a three-way catalyst. With diesel engines, long time they were able to go without a catalyst. Nitrogen oxides were reduced either by delaying of the injection timing, delaying of the combustion, or by exhaust gas recirculation. Both means reduce the peak temperature in a combustion chamber. However, they were associated with some very slight, but still some penalty in fuel consumption, less than 1% or maybe even several percent. Particulate matter was reduced by better atomization of the fuel, higher injection pressure, but also through better timing of the combustion. That's why instead of static timing, they were dynamic timing, electronically controlled engine timing, and lately common rail injection system where you can have multiple injections so you can phase the combustion. After treatment was added diesel oxidation catalyst, which reduced organic gases like carbon monoxide, some semi-volatile fraction of particulates, and most of the hydrocarbons in gaseous phase. Now, remember, most of the toxic effect of particulate matter is associated with a semi-volatile fraction on particulates. So diesel oxidation catalyst went quite a long way towards reducing particle toxicity or the whole toxicity of diesel exhaust. But the main breakthrough was diesel particle filters, which physically capture and periodically burn collected particles. With nitrogen oxides, we reached limits of combustion control without unreasonable fuel penalties, and now most modern engines use after-treatment, non-selective catalytic reduction, NOx storage and reduction catalyst, and selective catalytic reduction using some reducing agent, most likely ammonia. So far, most likely that ammonia is created by thermal decomposition of urea in the exhaust. Other solutions are emerging. We have lean NOx traps as one of the means to reduce nitrogen oxides emissions, and those function like a combination of a three-way catalyst and a NOx storage. NOx storage is accomplished by chemical transformation. For example, barium carbonate, which is in the catalyst, is changed to barium nitrate, NOx is captured and CO or CO2 is released. And that's during the normal lean burn operation of the engine. Periodically, you have to do something with the nitrogen oxides you have stored, because otherwise you would reach the storage capacity of the catalyst. And that's it. That's just like when you are wiping water that you spilled out or coffee with a rag, and periodically you have to wring it to remove the water, otherwise it's not efficient. So periodically you run the engine rich. What happens is you increase exhaust gas temperature, there are high concentrations of carbon monoxide in the exhaust, and under those conditions NOx are released from the storage, barium nitrate turns back to barium carbonate, and NOx are reduced by excess CO and hydrocarbons and hydrogen, just like in a three-way catalyst. It's a very simple device. It's a passive device. You control it by controlling the combustion in the engine. So from an engine manufacturer point, it's just some added engine controls, but no additional hardware. You use existing injectors that are in the engine. There are some side effects, some downsides. One of them is increased fuel consumption. You need extra fuel to create rich conditions to reduce nitrogen oxides. Also, ammonia and nitric oxide can be produced. So this is an example of vehicle driving in urban suburban traffic. You can see it's up to 60 kilometers per hour with some accelerations and decelerations up to about 2 meters per second squared. So it's a sort of moderate driving. You could keep your coffee in your hand. And cold engine, you have some engine out NOx. This is in red. And then you have some engine out NOx, but mainly in peaks, sometimes very low concentrations, and periodically you have regenerations. You can see during regenerations you have peaks of carbon dioxide during engine-rich operation. You also have peaks of methane. Unburned fuel is oxidized to CO2 and water, but methane is not, because it requires higher temperature to be oxidized than a catalyst. So you can see spikes of methane. You can also see spikes of N2O, nitrous oxide, that is created during regeneration. And here, there you have regeneration. Now, this, you have more dynamic driving, not higher speed, but higher dynamics. You see more decelerations and accelerations, maybe even a little more towards moderate than mild accelerations. And regeneration of a Lennox trap does not take place here. And you can see the emissions of nitrogen oxides gradually rising until regeneration again. Selective catalytic reduction. It's a old, well-known process from stationary combustion control. Selective catalytic reduction means it reduces that what you want to reduce without much reactions with something else, and that happens with a reducing agent, which is in this case ammonia. Ammonia, it can be stored in a liquid form and metered into the engine. It can also be stored, absorbed in some material in solid phase and released by heating it up. Ammonia can be also produced in a three-way catalyst under fuel-rich conditions, but the easiest way used so far, it may change, but so far, is to use water urea solution, which is liquid until about -10 degrees C. When you inject water urea solution into the engine, it decomposes first through isocyanic acid, which then decomposes to CO2 and ammonia. So you have an engine with exhaust, you have diesel oxidation catalyst, diesel particle filter, then you have metering of urea, or it is urea water solution known as AdBlue. That's a commercial name, and in the US they describe it as diesel exhaust fluid. And then you have a CR catalyst. In a CR catalyst, many reactions are happening. To simplify this, ammonia reacts with nitrogen oxides, ammonia is ammonia is oxidized, nitrogen oxides are reduced. The fastest reaction is when you have roughly the same amount of NO and NO2, and other reactions involving just NO or just NO2 are considerably slower. So it is beneficial to have higher concentrations of NO2 coming into a CR. You have to be very careful about chemical balance. If there is not enough ammonia, you have unreduced nitrogen oxides coming out. If you have excess ammonia, then you have ammonia coming out. Sometimes, because nothing is ideal, at a balance point, you get some nitrogen oxides unreacted and some ammonia slip. And under some conditions, on some catalysts, you have nitric oxide. The easiest way to operate it is you have NOx sensor here to know how much NOx is coming into the catalyst, and also on the outlet to know, have I done my work or not? Typically, to achieve very low NOx emissions, there is little bit excess of urea, and unreacted ammonia is oxidized in what's called ammonia slip catalyst. So ammonia is oxidized to nitrogen and water in ammonia slip catalyst. And it's the typical heavy-duty diesel engine after treatment: diesel oxidation catalyst, diesel particulate trap, urea injection, selective catalytic reduction, ammonia slip catalyst. Allows you to reach very low emission levels. Maybe even lower than on most of the passenger cars that drive on the road today. And then we have diesel particle filter. Where you have channels just like in a oxidation catalyst, but those channels are capped on one end or another. So through inlet channel, particles come in, and on the outlet channel, clean or particle-free exhaust comes out. This is how it looks like under electron microscope. What's called a soot cake is a layer of carbonaceous particles that are trapped by the filter. So the particles are not as much trapped in the body of the filter, in the porous walls, because the pores in a porous wall are much larger than the particles. It's just like when the snow is falling on a grid of a manhole on a sidewalk. The snowflakes are smaller than the openings, but as soon as a layer of snow builds up, then that's it. The filtration is almost absolute, and during that time the concentrations in a vehicle exhaust of particles, this is multiple runs with a heavy-duty truck just outside of Prague. This is already about 8 years ago. And the concentrations in the exhaust are even smaller than the background urban concentrations. When we left this truck with the engine off, but with the analytical instruments still on during a lunch, for that lunch period, the particle concentrations measured was about order of magnitude higher when the engine was off and the instruments were sampling from the exhaust, so the outside air was drawn into the tailpipe. So, very efficient device. This is just an example of the data from city bus driven for about 45 minutes, Braunschweig cycle with some brakes, a high NOx only until SCR is warmed up. After that, NOx is very low. You can see some increased emissions of N2O, but generally you have units of milligrams per second. So imagine milligram per second, that's less than 100 milligrams per minute. Well, you are on the order of 100-200 milligrams per kilometer for a city bus. Doesn't work all the time. We took a tractor trailer fully loaded, and for 1 week we drove it around Prague to look at the effects of congested traffic. When the exhaust temperature drops below and the cutoff is roughly somewhere in the general vicinity of 200 degrees C, the ammonia or the urea no longer decomposes in the exhaust, so no ammonia is produced, so it's better to stop the injection of urea, and the catalyst efficiency starts dropping. So this is the vehicle speed. Note the two periods or multiple periods of traffic jams with the average speed of less than 10 km per hour. In red are NOx emissions in grams per kilogram of fuel while the catalyst is cold when we started the engine. Then NOx emissions per kilogram of fuel drop down order of magnitude, but periodically they increase when average speed decreases, or after the lunch break when the catalyst is cold, and during driving through heavy congestion. So that's a technical limitation of SCRs. Again, when you think about what testing conditions do you need to see are those technologies working, you have to know something about those technologies, how they work. So cold start of an engine, low load operation, transient operation will need to be covered during any test to meaningfully assess, is this device working under realistic conditions? And if it's working under those conditions, it will also work under ideal conditions. By the way, operation of a heavy-duty truck at highway speed is not steady-state operation of the engine. If you don't believe me, ride with me on a truck one day. Even very slight variation of speeds require either using full engine power or no engine power, and the speed doesn't change that much. So it's not steady state operation as people might think. Now, when we look at our diesel cars, the results are not that good. Most of Euro 5 cars under realistic driving produce more nitrogen oxides emissions than during a type approval test. And the same goes for a lower but still considerable portion of Euro 6 cars. This is the reason why this was investigated, and we have what's known as Dieselgate, because some of it a result of intentional adjustment or calibration of the engines by the manufacturers. Now, this is not a new thing. It is not that US EPA doesn't like European auto manufacture. US EPA doesn't like anyone who cheats on vehicle emissions, and this is an example from now it's over 20 years ago, of NOx emissions of a heavy-duty truck. You have accelerations, cruise, and during cruise you can see that under some conditions NOx emissions are increasing over what they are under more favorable conditions, where those are very slight variations of the truck operating conditions, very slight incline, and it produces higher NOx emissions. Well, that has to do with the engine control unit looking, am I being tested for emissions? Am I not being tested for emissions? Oh, I am not tested for emissions, so I will save a little bit of a fuel at the expense of very high increase of nitrogen oxides. Well, that increase of nitrogen oxides, unfortunately, is associated with very severe damages to human health. This is from Professor Nino Kinsley from Basel, Switzerland, with reference to a Nature paper by Susan Annenberg. So those are people that very carefully have reviewed what they are saying, and they claim that the global consequences of manufacturers circumventing emission regulations are about 38,000 premature deaths every year. That's a fairly high number. And as a reason of that, if the member states of European Union don't do anything about this, well, what can the cities do? The cities will say, well, obviously the emission standards do not work because they are being circumvented, and not much is being done to repair this. Well, then what is the result? What a city can do? The city cannot pass new emission standards, but the city can close the road to a traffic. And some cities are saying, hey, you are not able to keep your emissions low. Well, the only thing we can do is ban cars or certain types of cars from the cities. So if we don't take care of our engines, it could be that we will not be able to operate them in many cities. Well, luckily, we have good examples that technology is our friend. This is by the way, this is a CNG, natural gas powered bus. You can see this, you can see the fuel tanks on the roof. And when we have tested this diesel counterpart for a reference at the airport, we found that bus emits about 0.2 grams per kilometer NOx, which is much better than most Euro 3, Euro 4, Euro 5 cars per kilometer, roughly about comparable with Euro 6 cars per kilometer real-world performance, not laboratory results. Now, that technology limit is being pushed down even further. In the US, it was proposed that the current limit of 0.2 grams per brake horsepower hour, now horsepower is 0.746 kilowatts, so 0.02 grams per brake horsepower hour corresponds to about 0.027 grams per kilowatt hour. And this translates to on-road emissions, trucks and buses, to between 20 and 40 milligrams per kilometer. The current Euro 6 standard for cars is 80 milligrams per kilometer. And there is some tolerance for real driving conditions. By the way, the current standard for US trucks and buses for heavy-duty engines is stricter than European standard. It is 0.2 grams per brake horsepower hour, which is 0.27 grams per kilowatt hour, and Euro 6 standard for transient limit is 0.46 grams per kilowatt hour, which is not double but close to double. And this proposal has been reviewed very carefully, and the conclusion was that it is technologically feasible, and there might be some downside. We might have to pay some money, and we might have to consume a little more fuel. The fuel efficiency might drop slightly. And one of the largest engine manufacturers, Cummins, they have issued a study, an opinion, an assessment, saying that with current technology we can go below, and this is 5 years old, we can go below the current standard, and if we go towards the proposed standard, you will see some penalty in CO2. However, improved developments in the engine are supposed to reduce CO2 emissions, to improve the engine efficiency, so that penalty might not be as high. This is still under a debate, but one thing that is clear is this bus, which you can see, it was a good representative. It was pulled from the traffic, from regular operation, and it is a representative of the buses that are going around in Prague, and maybe the cleanest vehicle in terms of NOx and maybe even particulate matter could be per kilometer city bus. It's better than most Euro 5 and Euro 6 diesel cars. So the future of our engines depends on how well we can manage the emissions. We have the technology to do that, and we have to do it to protect human health. If we don't do it, engine use in the cities might be restricted for the protection of human health. Now, in order to do that, we have to measure, we have to test, we have to know what the emissions are. We need to develop new technologies, calibrate engines. If we have new fuels, new operating strategies, new combustion mode, new types of after-treatment devices, we have to assess their emissions performance. That's why we do research testing on selected small amount of vehicles in the laboratory for research, for engineering, for type approval. Then we equip vehicles with onboard diagnostics to diagnose emission problems. Also, we check on those vehicles, do they last so many kilometers per or miles? Does the technology hold? Do the catalysts deactivate, or do they perform adequately after 500,000 kilometers? those testing you do with portable onboard emission instruments mounted in the vehicle you are testing, but also you can have your instrument in another vehicle and drive behind. That's called a chase vehicle. You put instruments in a chase vehicle and you follow the vehicle you are measuring. That's on-road test. And then you have inspection and maintenance and remote sensing and various means of quickly and inexpensively assessing the emissions of individual vehicle, because emissions over the time increase exponentially, but on most vehicles that increase is small, but you have some amount of vehicles. This is an example of 20 natural gas buses. You get some amount of vehicles that produce high emissions. Bus number 18 here. And the emissions of that are about 10 times the average of the clean ones. So if you have 10 vehicles and 1 out of 10 has 10 times the emissions, you just doubled your fleet emissions. So you have to do something about high emitters. So you need to detect them through either periodic or random inspection and maintenance tests. Simple, inexpensive tests just to say low emissions, high emissions. You are okay, you go to the repair shop. So we have to assess, why are we testing? What is the goal of the testing? What do we want to get out of it? And based on that, decide the method and the instrumentation. So during next part, we will look at the emission measurements techniques.